Welcome to non-homogeneous heat conduction problems. So the general idea here, again, we are looking at a metal rod. And we are considering temperature, U, at time t, and position x along the rod. In this case, we say the rod has length L. This time around, instead of holding the ends at 0 degrees, we're going to hold both the ends at whatever temperature we wish. So one end, or the 0 end, of the rod is held at U sub 0 degrees. And the L end of the rod, x equals L end, is held at U sub L degrees. So again, this is a change from our holding the two ends at 0. The other thing we have is we have an external heat source. So we also have an external heat source. Which transfers heat at a rate of h of x at position x along the rod. Essentially, this becomes as our differential equation is no longer considered to be homogeneous. So the non-zero boundary conditions complicates the problem just on its own, and this h of x can also complicate the problem. So just sort of translating this problem into symbols, our partial differential equation, our heat equation, becomes the partial with respect to t of u is equal to a squared times the second partial with respect to x of u plus h of x. Then we have our boundary conditions. u of 0t is equal to u naught, and u of lt is equal to u sub l. Again, we have initial conditions. I didn't specify them this time. The initial condition is that the initial temperature, u of x0, the initial temperature at x equals 0, is given by f of x. I need to update my screen. All right, so again, we have our same initial condition we're used to, which is the initial temperature at position x. In other words, u of x0 is equal to f of x. So in finding the solution for this, we are going to go ahead and assume that our solution comes in two parts. So let's go ahead and set u of xt to be equal to v of xt plus q of x. And then we are going to find q and v that make this problem easier to work with. So this means that we have, since the first partial with respect to t of u should just be equal to the first partial with respect to t of v. We also have the second partial with respect to x of u is equal to the second partial with respect to x of v plus q double prime of x. So the heat equation, or the equation, becomes the partial differential equation becomes, we have the partial with respect to t of v is equal to a squared times partial with second partial with respect to x. So that's second partial with respect to x of v plus q double prime of x. And then, so that's our a squared times second partial with respect to x of u. And then we end with a plus h of x. Updating my screen one more time. So again, we have that first partial with respect to t of v is equal to a squared times, in parentheses, the second partial with respect to x of v plus q double prime of x, end parentheses, then plus h of x. So we can rewrite this as vt is equal to a squared times the second partial with respect to x of v plus a squared times q double prime of x plus h of x. So what we are going to do is we are going to set, to make this simpler, let's go ahead and set a squared q double prime of x plus h of x equal to 0. Then we have first partial with respect to t of v is equal to a squared times the second partial with respect to x of v. And this looks like the original homogeneous heat equation we were working with. So I'm going to sort of box the pieces that we're playing with along here. Then note that you are looking at our boundary conditions. So translating our boundary conditions. We had u of 0t equal to u naught should be equal to v of 0t plus q of 0. So we have the v of 0t is equal to u naught minus q of 0. Similarly, u of lt is equal to u sub l should be v of lt plus q of l, since we assumed u was equal to v plus q. So we have that v of lt should be equal to u sub l minus q of l. So if we go ahead and set q of 0 equal to u naught and q of l equal to u sub l, then we get that v of 0t would be equal to 0, would be equal to v of lt. So again, boxing these two conditions to keep with us. We have our equation in Q results in a familiar equation in V. We have our boundary conditions on Q result in familiar boundary conditions on V. And then finally, our initial condition. So translating the initial condition. We had u of x comma 0 is equal to f of x, but this should also be equal to v of x 0 plus q of x. And so what this means is that our v of x 0 should just be equal to f of x minus q of x. So here, our V, we have boiled it down to a homogeneous heat conduction problem in a rod with 0 boundary conditions, and then an initial condition, which is simply a function. And we have a way to solve for our Q. So what we get is putting this all together. We have the solution is u of xt is equal to v of xt plus q of x, where q satisfies, or q is a solution to q double prime, a squared q double prime of x equals negative h of x, if we rearrange that, or a squared q double prime of x plus h of x equals 0. With boundary conditions, q of 0 equals u naught, and q of l equals u sub l. Note, if there is no external heat source, if we just have the ends fixed at non-zero values, this solution is just a straight line. And then, so just note, if there is no external heat source, then we just have q of x would be equal to the line with y-intercept u naught. So we'd have u naught plus, and then slope ul minus u naught all over L, then times X. So, right, if we have Q double prime just equaling 0, we know that it's a line. We have 2 points on the line, so we can figure out both its slope, and in this case, we are given a y-intercept. If h of x is non-zero, then we do have to put in a little work. Furthermore, so this is Q, and V is the solution to first partial with respect to t of V equals a squared times the second partial with respect to x, with V of 0t equaling V of LT equaling 0, and V of x0 equaling f of x minus q of x. So we know how to solve this. We have the V of xt is equal to the sum from n equals 1 to infinity of c sub n times e to the negative a n pi over L whole thing squared t times sine of n pi over L times x. And our c sub n's are 2 over L times the definite integral from 0 to L. This time, instead of f of x, our initial condition was f of x minus q of x. So we'll do f of x minus q of x times sine of n pi over Lx dx. So this is our final solution. Again, we do have the formula for our V of xt now, since that was just our homogeneous with 0 boundary conditions heat condition case. So this is how we can go about solving the non-homogeneous case for heat conduction in a rod.